Welcome to the Picture Language Seminar. We're tremendously happy today to have Seth Lloyd, one of the pioneers in quantum information and quantum computing. He's known in the world of algorithms, and today he's going to tell us, Seth is professor at MIT, and today he's going to tell us about quantum algorithms for topological and geometric analysis of data. So Seth, share your screen.
Great, let me do that. Here, first I'll actually share. Can you see that this is the paper on which this is based, and Crystal is going to sorry, let me here's this paper. This is with Paolo Zanardi and Silvano Gonarone. It's from Nature Communications, and it was published 5 years ago or so. So if you want to, and Crystal, I sent this paper to Crystal, so she's going to put it on the website so that if you want to read it and learn more about the methods we're talking about, then you can find it in this paper. But let me share the, whoops, sorry. I'm trying to now share the talk. Won't let me do that. Don't ask me why this is happening. Okay. Let's try this. Sorry. Let me, excuse me, I'm not very good at talking and chewing gum at the same time. So, okay. Let me try it. Now, let's try it again. Okay. All right, can you see this now?
Great, everything worked.
Good, great. So, I'm going to tell you today about this quantum algorithm for topological analysis of data. First of all, it's a great pleasure to be here. This is a great seminar series, and I've really been enjoying it. It's unique, actually, in terms of having just fun stuff every week. And thank you, Arthur, for inviting me to give a talk here. This is a talk about quantization of a classical algorithm, a set of classical algorithms for doing topological analysis for data, which is kind of funny, really, right? Because one thinks of data as being this discrete digital kind of thing. So, and one thinks, so I tend to think of topological things, as features that are invariant under continuous transformations. It turns out that there are some very powerful and useful and interesting methods for doing topological analysis of data. And these algorithms, I was introduced to them about, I don't know, about 10 years ago. Mario Rossetti, the head of the Institute for Scientific Interchange in Torino, sent me a series of papers on these algorithms, and I was unable to understand them. So I tried reading them and I failed. I don't know if you guys have this happens to you, but this happens to me a lot. I start reading a paper, I think it's going to be really interesting, and I just get completely bogged down and I just can't do it. And then I come back to it and I try again and I fail again. And my friend Paolo Zanardi was having the same problem with these papers. So we decided finally to sit down, and if we could do it together, maybe we could make it work. And we were in Benasque in Spain, and every morning we'd go have a cup of coffee and go for a hike, and we'd talk about it. And eventually we figured it out. We realized that you could make very nice quantum versions, a simple, I don't know about nice, but simple quantum versions of these algorithms. And the idea is, this picture shows, you have data, and you have data in some kind of high dimensional space, and the data is represented by discrete points in a high dimensional space. And if you look at this, can you see my pointer, by the way? this over
Really,
here,
it's not very visible, but we see it.
okay. Anyway, yeah, sorry, I should have, too late for me to make it larger. This data over here is here you have these points in a high dimensional space, and it's just a hole in the high dimension. You can see that even though it's discrete, that there's a kind of a hole in the middle of the data. And so how do you actually figure this out? How do you identify this hole? And these methods work essentially by triangulating the data or turning it into a simplicial complex. And here's the same data in which I've connected neighboring data points via lines. And when you do that, you get a set of lines and triangles, a set of simplices, actually. And now when I've connected this data in this simplicial complex, you see that this simplicial complex actually has a hole in the middle. And then these methods from algebraic topology allow you to identify holes and voids and connected components and other topological features of data via what's called persistent homology. And I'll explain in a bit how persistent homology works, but it basically works in the way I just described. That is, you have a metric on the space of the data. You use that to construct a simplicial complex that connects neighboring data points. And then you look at the topology of this simplicial complex. And classically, this is a useful thing to do. It gives it the topology of the data, gives you all kinds of signatures of the data. And in particular, topology, the topological features of the data are those that are invariant under distortions of the data. So if you look at the topological features of the data and you say, oh, this data somehow got distorted in the process of collecting the data, it was distorted, or in the process of recording it, it got distorted, then topological features are those that are left over once you've actually, because the topological features are invariant under continuous distortions of the data, kind of by definition. And this is nice, but actually in very high dimensional spaces, if I have n data points, actually doing this analysis takes time order 2 to the 2 to the n. Actually, it's even worse than that. It's like 2 to the 6n or something like that. But 2 to the 2 to the n, which is a large number. And quantum mechanically, these processes are going to end up taking time order n cubed, where n is the number of data points, because we're going to take advantage of the ability of quantum computers to do linear algebra and things. In this case, it's going to be finding eigenvectors and eigenvalues, the quantum phase estimation algorithm, in exponentially faster than classical computers. And so this is a quantum algorithm that has an exponential speed up over the best known classical algorithms for this topological analysis. Anyway, I think I'm going to stop there for a moment and ask if people have, I'm going to stop sharing for just a second, and ask if people have questions that you'd like to put in the chat, or if you'd just like to, identify yourself and ask a question at this point. Arthur says that he likes people to identify themselves in person, insofar as this debased medium allows one to ask a question in person. Okay, if there aren't any questions, and just as things go on, just please pop your questions into the chat. And when I see something come to the chat, I'll immediately I'll read it, and then I will answer it as things go on. Okay, so let's go back to this screen sharing. So can you see the screen sharing now again? Okay, good. So let's, moving onward here, let's go and take a look at how this works. So let me just actually remind you, as kind of an introduction of how things work in quantum machine learning. Quantum machine learning is now, this is a field I've been working on now almost for 10 years, since my postdoc Patrick Rebentros came and said, hey, let's do things like, quantum support vector machines and stuff like that. And it turns out that quantum computers have lots to offer when it comes to machine learning. The kind of very simple reason is that, simple and obvious reason is that quantum systems are good at generating funky patterns in data. I mean, quantum systems famously generate patterns in data that are very hard to generate classically in things like, the EPR paradox, and more recently in the unfortunately named field of quantum supremacy. And so then, but if they can generate patterns in data that are hard to generate classically, maybe they can actually recognize patterns in data that are hard to recognize classically. And that actually turns out to be true. And the methods for doing this, essentially, there are quite a few methods that operate using the ability of quantum computers to do linear algebra more faster, exponentially faster than classical computers. And a lot of these methods work as follows. You have some data, which is, say, some vector in a very high dimensional space, and then you map it into a quantum state. The ordinary way of doing this is via quantum random access memory, but there are lots of other ways of doing it. And then there are things like, for instance, you can take quantum Fourier transforms, or you can do data fitting, like least squares fitting of data turns out to be equivalent to matrix inversion, which is, we're solving linear systems, which is exponentially faster on quantum computers. You can do things like support vector machines. There's some very nice recent papers, including a lot of experimental papers coming out of places like Xanadu and IBM about how you essentially quantize kernel methods. Quantum systems are very natural for doing kernel methods, because kernel methods operate by embedding data as vectors in high dimensional Hilbert spaces, and then using the natural metric on the Hilbert space to distinguish between, say, two clusters of data. And of course, quantum systems supply high dimensional Hilbert spaces. That's just what they do. And support vector machines are nice ways of doing this. You can do things like principal component analysis. This is exponentially faster on a quantum computer. Today, I'm going to talk about topological invariance. And there are all kinds of fun things. You can apply this to methods of quantum finance. Actually, you can apply these topological methods. Turns out that a common application of these topological methods is, in fact, to look at financial time series, where you're looking to see if the topology of the time series is changing as a sign that, there's going to be a crash or something like that. Anyway, so quantum computers are good for various kinds of machine learning applications. And I'm going to go back. If there aren't any questions, I'm going to check to see if there are any questions now. Are there any questions? Nobody's popped anything in the chat. Pop something in the chat so I can answer some questions. Okay. But I will now tell you, if there aren't questions, then I will tell you how these methods work, because they're pretty fun, actually. Again, they're very natural. These topological methods work very naturally in the context of quantum machine learning. But please put something into the chat if you have a question. I will say that I can't actually see the chat when I am sharing. So I'm going to periodically stop sharing and then look into the chat to see if people have questions. Okay. Heading back to this now. Let's take a look. So how do these methods work? So persistent homology, it sounds fancy. But it works the way I described. You group, essentially, you have some discrete data and you create a discretized simplicial version of the manifold on which this data lies. So the idea is the data lies on some manifold. We don't know what this manifold is. We'd like to figure out topological features of this manifold. And the idea is that we're going to group things at different scales. So basically, the picture is as following. We're going to, a simple way of doing this is what's called a Vittorius-Reeps complex in topology. That is, I just make a little epsilon ball around each of my discretized data points. And then I'll connect two data points if their balls overlap with each other. And here, if epsilon is very small, you see here's my data, and the balls are so small that they don't overlap with each other. And so nothing gets connected to each other, and the data is all holes. You don't see this hole. Here, however, when I make epsilon larger, then these balls start to overlap with each other. And if I connect neighboring data points that actually have overlapping where their epsilon balls overlap with each other, as in this picture right here, then I get a simplicial complex and this whole emerges. Now, if I look at this hole is going to persist as I make these epsilon balls bigger and bigger. The hole is going to persist, but the hole is going to get smaller and smaller and smaller. And eventually, when these balls get too big, everything is connected with everything else, and the holes go away. So, but in the intermediate region here, there is, as I group the data at different scales, there's a set of regions where this hole shows up, and then it persists over a wide range of grouping scales. And the point about persistent homology is we look at things like voids and holes. These are homological features of the data, and topological features that persist over a wide range of grouping scales are considered to be actual features, topological features of the data. So that's how these methods work. And I'll just say, are there any questions about this before I go into the mathematics of how we can make a quantum algorithm? So I'm going to stop sharing. Anything in the chat?
It sounds like you need to get analysis into the topological picture too.
Yes, absolutely. So in fact, these particular methods, in fact, overlap with a lot of very interesting mathematics. And really, I'd be very interested, since this is a mathy kind of crowd, if I may say so. This is a compliment, not a mathy kind of crowd. I'd be very interested in ideas of how these ideas might be extended. I mean, the particular methods that we're going to talk about have overlap with various aspects of geometric theory, like Hodge theory, and algebraic topology is a huge field. So it seems reasonable to hope that various aspects of linear algebra and quantum computing might be able to give us insights in other aspects of algebraic topology as well. So, so I'm going to leave time at the end to make sure that we have time to talk about this. Okay, so let me go back to, don't see any questions, so let me go back to sharing the talk here. Okay, so how do these methods actually work? All right, so the way that we're going to do this is having constructed a simplicial complex. So it's a simplicial complex is, we're going to actually look at simplices. Here I'm just drawing two-dimensional simplices, which are triangles. But this method works for any simplices of any order. So essentially the way a simplex works, a simplex is just simply a two-simplex is a set of 3 points, each of which is connected to each other. And a k-simplex is a set of k points, each of which is connected to each other. So for instance, a three-simplex, sorry, a two-simplex is a three-simplex has 3 points, and a four-simplex would be 4 points connected with a tetrahedron. So I have 4 points, they would be connected in a tetrahedron. And a k-simplex is just k points that are all connected with each other. So 5 points is a tetrahedron is, the three-dimensional analog of a triangle. 5 points all connected to each other is the four-dimensional analog to a tetrahedron, etc. So k-simplices are just k points that are all connected with each other. And the way that we can encode these as a quantum state is we simply say if we have n different points, here n is equal to 6, we simply have ones in the points that are all connected to each other. So here we have 6 possible points, and 6 points, and these 3 points, 1, 2, and 6, are all connected to each other with a simplex. So I simply encode this as a state where I have a 1 in the 1 slot, a 1 in the 2 slot, and a 1 in the 6 slot. So sorry, I'm just going to change position here so I can get a little more light. You can still see this here, I hope. So here's this one. This is a three simplex here. It's 1, 2, and 6. And the way the fundamental algebraic object we're going to use here is what's called the boundary map. And the boundary map, if we're encoding simplices as vectors in a high dimensional space. So here we've naturally encoded this 3 simplex as over out of one of the over n possible points, 6 possible points, we encode it as a vector in a 2 to the 6th dimensional space. So this is a very natural thing to do, and this is in how the simplicial homology works. We take topological objects which have a connectivity, and we map them into a high dimensional vector space. And then we're going to change our questions, our topological questions, into algebraic questions by asking questions in high dimensional vector spaces. And that works kind of nicely, as we'll find out. So what is the boundary map? The boundary map takes a simplex and it constructs the points on its boundary. So it creates a vector, which is the sum, in this case, the quantum superposition of the 2 simplices, which are just lines, which are the boundary of this simplex. So in this simplex right here, there are 3 points on the boundary. There's the 1, 2 line. There is the 2, 6 line, and there is the 6, 1 line. And so what the boundary map does is it just constructs a uniform superposition of the points on the 2 simplices on the boundary, the edges in this case, but every other one gets a minus sign. So alternatingly, you apply a minus sign. Now, why do you do that? The reason is that if I apply the boundary map now to a collection of simplices, say here I have these 2 triangles that share an edge. Now we're in the lower left-hand corner. So now instead of here I have 2 triangles or 2 simplices that share an edge. This gets mapped in this geometric, in the algebraic picture. This becomes the sum of these 2 simplices. Here we go. It's like 1, 1, 0, 1. 1, 1, 0, 1 is this 1, 2, 4 simplex. 0, 1, 1, 1, that's this 2, 3, 4 simplex. And when I actually take the boundary map acting on this sum, it's just a superposition of these 2 simplices, what we find is that the shared edge is going to cancel out. So if you look at this here, I take this boundary map acting on the sum. Here's this simplex. This is mapped to 0, 1, 0, 1. That is the 2, 4 edge. And then there's the 1, 0, 0, 1. That's the 1, 4 edge. It has a minus sign. And then there is the 1, 1, 0, 0. That is the, which edge is that? That is the 1, 2 edge. And then if you have the 2, 3, 2, 4, the 2, 3, 4, 1, we find that we get 0, 0, 1, 1, minus 0, 1, 0, 1, and then plus 0, 1, 1, 0. And these 2 cancel out. If you look at this right here, the 0, 1, 0, 1 cancel out. And the minus sign kind of magically, it's not magic, it's math, but I always find it kind of magically, it removes the interior edges of this and simply leaves us with this 1, 2, 2, 3, 3, 4, 4, 1 edge of the actual boundary of this, what's called a chain of simplices that correspond to a bunch of simplices that are connected together. So that's why this is called the boundary map. It has this feature that it kind of in this magical sort of fashion, or at least it seems magical or amazing to me, it removes the interior edges, because basically the point is that they get traversed once in one direction, once in the other direction. And so they always get a minus sign relative to each other. And so they cancel out. So this is this boundary map, and our people, this is actually very important, the key object. So I'm going to stop sharing right now and ask people to, if they have questions about that. First of all, are people here familiar with this? Like, raise your hand if you're familiar with this before. Great. I heard I saw a hand raised. Do you want to ask a question?
Yeah, it seems like you're choosing the negative signs almost arbitrarily here in order to force the removal of the inner edge. So I just, this is not super familiar to me. So maybe you can try to explain again how these negative.
Yeah, so if it's simple. You have a list of the edges, right? It's just a list of the simplex has consists of a list of vertices, all of them connected to each other. Okay, and let's assume that the list always occurs we have the list, the vertices are 1, 2, 3, 4, 5, 6 up to n, and we just list the vertices in their ascending order. Okay, so like 1, 2, 4. So I get an edge by omitting a vertex. So in 1, 2, and 4, here's a triangle. It's 1, 2, and 4. If I omit 1, then I get 2, 4, which is one of the edges. If I omit the second one, which is 2, I get 1, 4, which is another of the edges. If I omit 4, the third one, 4, I get 1, 2, which is the third one of the edges. Okay, is that okay? Like I can actually, this is kind of on this.
Yeah, absolutely.
Right.
Bert Halpern has a question.
So and what you do is
Bert Halpern has another question.
Okay, good. So let me.
My question was the same question. How do you assign signs?
So you see, I get here on the top of this right here. If you can see this, the first edge I get by omitting 1. I have 1, 2, 6. Here's this vertex. So I first look at the edge that I get by omitting the first one. That's this 0, 1, 0, 0, 0. That's the 2, 6 edge. That gets a positive sign. Then I look at the edge I get by omitting the second one. The second one is 2, so that's the 1, 6 edge. That gets a negative sign. Then I look at the one that I get by omitting the third vertex.
Why? Can you explain why? Again?
And then that gives the third vertex, that gives this 1, 2 edge, and that gets a positive sign. So the rule is if you get a negative sign for every other edge. For every other edge, what you get by omitting each vertex in ascending order. Is it clear what the rule is?
Yeah, that's clear to me. Yes, thank you.
That's clear. Okay,
Yeah. I have a question. So how do you traverse the edge? Clockwise or counterclockwise, or it doesn't matter?
Right. So that's right. So that's important. So the way that we've done this is we made a that's a very important question, right? These simplices are oriented, right? And they oriented. We chose when we said, okay, we're going to list all the simplices, all the vertices, 1, 2, 3, 4, 5, 6. So we picked an ordering. We can pick any ordering we want, but we picked an ordering. Then when we describe a simplex, this 1, 2, 6 simplex, we listed the vertices in ascending order according to the original order, and that gives it an orientation. So it's oriented 1, 2, 6. So it's oriented like that, going around in that direction. Okay?
Yeah, so this is applicable to only orientable manifolds, not Mobius strip and kind of things, right?
Right, actually, right. That's a very good point. I think well, actually, yeah. Right, so that's a good question. You got me wondering there. Right, you mean, so it's okay. I mean, if I look at submanifolds, so you're saying if I have a submanifold and it's not orientable, like a Mobius strip, then this is going to get messed up. You're probably right. That sounds correct to me. So let's just assume that we have an orientable submanifold. So then this boundary map, if we have an orientable submanifold, because each of the simplices in it is orientable, this rule of having alternating signs, for this rule means that these interior edges get canceled out, because each interior edge appears twice, and it appears with opposite sign because of the choice of orientation. So that's why one chooses it in this way. And by the way, I've said this just for these, this is just two-dimensional ones, but of course it works for three-dimensional ones as well. If I have three-dimensional simplices, which are tetrahedra, then the internal triangles will also cancel out. This is great. So thank you for asking these questions. These are extremely important questions. All right, is this okay? I'm back. I stopped sharing so that if people want to talk about it some more, because this is the key point, really. That's the feature of this boundary map is we're basically just going to get everything by finding singular vectors and singular values of this boundary map. And that's, in fact, I just told you how the algorithm works. So it's very important to understand what this boundary map is, because after this, it's going to be pretty straightforward. Okay, sounds to me like nobody's seems to be, Bertrand's hand.
Second boundary is 0.
I'm sorry?
Boundary squared is 0.
Okay, good. All right. All right, I'm not seeing anybody else's hands up. And so I'm going to go back, and now, since actually this is actually the key point, right? So since people seem to have gotten this key point, now we're in good shape. So everything that we're going to do from now on is just going to say, okay, we have this boundary map. It's a linear map. And in fact, all we're going to do from this point on is we're going to find eigenvectors and eigenvalues, or actually the boundary map it's not square. So we're going to find singular vectors and singular values of this boundary map. And it turns out that therein lies the answer to doing things like finding these holes and these voids and counting the number of holes and voids at all dimensions. So let's see how that works. All right. So now here, this is the key point. The key point about these boundary maps is that these holes and voids, the representatives of the homology, they correspond to sets of simplices that are boundaryless, but they are not themselves boundaries of anything. So let's look at things that are boundaryless but are boundaries. So the point is that the boundary of a boundary is 0, right? If I have something that's a boundary, like for instance, here are a set of edges. They are the boundary of this set of 5 simplices. These red edges right here and the thing on the left, these are the boundaries of these 5 simplices. Because it's the boundary of these 5 simplices, this submanifold, it itself doesn't have a boundary. It's topologically a circle, so there's no boundary. But it itself is boundary of something in this discretized manifold. So it doesn't have a boundary, but it itself is a boundary, and so it actually doesn't correspond to a hole or a void. In fact, it doesn't correspond to hole because it's filled in, right? If I were to remove these 5 simplices and then look at this edge right here, then it would indeed be a hole, because I removed the stuff in the middle, and it wouldn't be the boundary of the anything because it's a boundary just of the hole. So the things that we're actually looking for that corresponds to holes and voids are things that are boundaryless, but they're not themselves boundaries. So here in the torus, we have things like this that are, this is the torus, it's just a sheet, it's not the filled in torus. And if I look at this line right here, it is boundaryless, it goes around there, but it's not the boundary of anything on this 2-dimensional sheet that is the torus. And similarly, if I were to draw another hole that goes around the whole of the donut right there, that would also be boundaryless, but it wouldn't be the boundary of anything because it's the boundary of the whole. So at dimension k, for k simplices, what we're actually looking for, the way that we're looking for are things that are boundaryless. That is, boundaryless things are things that are in the kernel of the boundary map. Because if we go back to the previous page, if I take something that is boundaryless, it doesn't have a boundary, then I apply the boundary map to it, I get 0. So things that don't have a boundary are in the kernel of the boundary map. But we want things that are not themselves boundaries. So they're not in the image of the one higher dimensional boundary map. So mathematically, the objects that we're trying to find are objects that are in the kernel of the boundary map at dimension k, but they are not in the image of the boundary map at dimension k+1. So these themselves, these objects are the representatives of this discretized homology. They represent things like holes and voids, because they are things that are boundaryless but don't have boundary. And the number of holes of dimension or voids of dimension at dimension k actually is the dimension of this space. So with a number of linearly independent such objects, because we've mapped these objects into states. So as this is a kind of a mathematical point, I'm going to go back to the previous slide here. Actually, I'll leave this slide up here. I'm going to stop sharing, and I'm going to ask people to ask questions, because this is, this is really the central conceptual part, is that representatives of the homology are these things that are boundaryless, but are not themselves boundaries of something else. And the mathematics of actually trying to count them, find them, and count them, and the number of such at dimension k is the kth Betti number. So we're going to try to find the representatives of the homology, and we're going to try to count them. So we're going to try to find the Betti numbers. And to do that, we're going to ask linear algebraic questions. We're going to try to find questions. We're going to try to identify things that are in the kernel of the boundary map. But we're going to try to exclude things that are themselves boundaries. So I'm going to stop sharing now. And I bet I wouldn't be surprised if people had some questions.
Yeah, what is that indexing k+1?
Right. So great. So let me, I think if I go back, I can, let me go share again. Right, good question. So k tells me the boundary map at dimension k is the dimension of the simplex that I'm looking at. So here we have these 3 simplices which are in 2 dimensions. So a k simplex has k vertices. So here I should have actually had here, this D should have had a D sub 3, because k is equal to 3 here. And if k was 4, then I'm looking at 3-dimensional simplices, which are tetrahedra, and the boundaries are going to be 2-dimensional spaces. So k labels the dimension of the simplex. Does that make sense?
Yeah, it makes sense, sure.
Great. Okay, I'm going to stop sharing. Thank you very much. That was really remiss of me not to say what that was. Other questions here? Oh, I see Vladimir Karepin here. Hi, Vlad. How are you?
Hi. Good to see you. Your explanation are very clear and very consistent. So thanks for explaining.
Hi, great to see you. Anyway, but we can chat afterwards. This is the time for questions.
Definitely.
Okay, so are people okay about this?
What happens when k equals n? When you don't have any extra, so how do you do the d k+1 in that case?
Oh, okay, that's a good question. Let's go back. When k equals n, great. Let's go back to sharing. So when k equals n, right, I think the point is that when K is n, there can be only one n simplex. It's where all the points are connected to each other, right? That's what, so everything's connected to everything else. It's an n simplex, and its boundary is the set of all possible n-1 simplices. And so it's the set of all simplices where you've omitted one vertex. And then, of course, as usual, you have to have the alternation of signs because of the orientation. And the n simplex, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to n. And so that's the ordering. So yeah, great question. I'm going to stop this. So I'm going to go back here and stare at this for a second. But I'm going to stop sharing. Yeah, good question. Any more questions about this? These are great questions.
So simple question, since you're acting on states, you can define the adjoint of the boundary. Does that have a good significance?
Yeah, so actually the adjoint of the boundary map is going to be pretty essential here. And in fact, let me, might scribble on some pieces of paper at some point along the way here, just to show how this works, because I don't recall if I actually wrote it down. So let me go back to sharing screen. I'm going to share the screen. So the adjoint of the boundary map is very important because, and let me actually say what we're going to do here is, because what we're actually going to do is we are going to we're going to actually look at the we're going to apply to do quantum phase estimation. We're going to, let's stop the sharing. If you can actually see, if you can see if you're looking at this by looking at me, we're actually going to look at maps that are of this form, which are we have the boundary map and its adjoint and the off diagonal. So we're going to look at Hermitian maps of this form, and we're going to apply quantum phase estimation. That is, we're going to find eigenvectors and eigenvalues of maps of this form that have both the boundary map and its adjoint in it. And these are going to turn out to the kernel of these maps of this operator, of this matrix, this Hermitian matrix. The kernel of this map is going to contain the objects that we want, and the dimension is going to actually the dimension is going to be the Betti number. It's going to be the number of representatives, of independent representatives of the homology. So that's a kind of like, that's how it works out.
So a mathematician would say you're just describing a variation of index theory.
Yeah. And this is it's right. Yeah, this is right. Yeah, this is like, I should say that, you know, I'm not, you know, a mathematician or even a mathematical physicist. Halfway through my undergraduate degree at Harvard, I've been thinking of majoring in math, and I realized I better just do theoretical physics instead, because I realized that there were so many other people I knew who were better at math than I was. This was actually, but of course, this was part of this was because I was taking Math 55, and 3 out of 5 members of the US Junior Math Olympiad team were in Math 55 that year. So it was a little intimidating. It also had the feature, it was Math 55 that year. I don't know how many of you out there have taken Math 55, but it's a hard course. And in fact, it's the only course at Harvard that MIT students are not allowed to take, because otherwise they would challenge themselves by taking it. There'd be too many students in Math 55. And the first test, the first midterm came back, and, you know, I'd studied really, really hard for this. And I was like, oh gosh, you know, I don't think I did very well in that midterm. And indeed, when I got back my paper, my midterm exam paper, I'd gotten 12 out of 100. And I said, okay, this is it. Like, I'm going to fail this course. This is just not going to work. And so then the teacher, who was Hiyosuke Hironaka, by the way, very wonderful guy, I'm sure that people there knew him. He said, okay, I've handed back your tests. So I thought people did very well. You know, actually the class average was 8 out of 100, but I was impressed by what people knew.
Did your advisor give you any advice?
Did my advisor, that is to say you, Arthur? Arthur was my undergraduate advisor. Actually, but I don't think you were my advisor freshman year though. I think you might have given me advice like, I don't know, stay the course, it'll work out. You were a great advisor, Arthur. I survived. By the way, I have to tell since we're on the topic, I have to tell a Hironaka story because he was a Fields medalist, right? And a very, very brilliant mathematician. And he had this really bad habit though. He would say in the course of teaching, he'd be proving some theorem or other. And then he would say, it is obvious that, and then, you know, he was about to say something that he thought was obvious, but then he would go, He was thinking maybe it's not so obvious. So then he'd go to a little corner of the blackboard and he'd do a little calculation in the corner of the blackboard. He'd go, and then he'd erase it. And then he'd say, it is obvious that, and say what he was going to say. This is extremely demoralizing because, you know, here he's saying it obvious. The man's a Fields medalist, for God's sake, and it's not even obvious for him. He's lying that it's obvious. It wasn't obvious. He had to do a little calculation. Anyway, so, okay, anyway, he was a great guy. It was very fun. So let me go back to none of these things are obvious. And it really took me a long time. You know, it took Paolo and me a long time to figure out what was going on here. So if it's not obvious to you, I'm trying to explain it in a way that makes some kind of sense. But so let's actually see what actually happens. I mean, none of this is obvious at all. It's not obvious. So, but we're now going to actually say, so since I want to leave time for discussion, we're getting there. We're near the end here. We're going to look for chains of simplices, that is superpositions of simplices. They lie in the kernel of the boundary map, but not in its image. The kernel of the boundary map at dimension k, these are k simplices that are annihilated by the k-dimensional boundary map, but they're not in the image of the boundary map at one higher dimension. So they're not the boundaries of some chain of simplices that get mapped into a k-dimensional chain of simplices at that dimension. So that's what we're looking for. And how do we do that? So here's how we do that. And you can see that I went 2 slides and that's the summary. So this is the last real slide here. All right, so what do? So at each grouping scale, epsilon, we construct the chain, the quantum superposition of all possible simplices that actually exist in the complex. So here we define the state S sub k. It's just a sum of all k simplices that are actually in our simplicial complex. So it's, as a quantum state, it's just all simplices in the complex at that scale. And now what we do is we are using the quantum phase S algorithm to decompose S sub k in terms of the eigenvectors of what is called the combinatorial Laplacian. So the combinatorial Laplacian, there are 2 terms in it. Let's look at the k term. The k term, the boundary map maps things down from that level k to dimension k minus 1. And then the adjoint map maps them back up to level k. And then these are things, if you're in the kernel of this, then if you're in the kernel of dk, then you'll also be in the kernel of this operator right here. Now, the other part takes things from k plus 1, it maps them up and then maps them back down again. And so this is the thing which is going to ensure that if you're in the kernel of this, if you're in the kernel of this, you're boundaryless. So if you're in the kernel of the dk dagger dk part, you're boundaryless. And if you know the kernel of dk plus 1, dk plus 1 dagger, then you're not the boundary at something at level k plus, not the boundary of something at dimension k plus 1. Phew, that's what I wanted to say. So if you're in the kernel of this simplicial Laplacian, then you're boundaryless, but you're not a boundary. And so you're a representative of the homology, and the dimension of this kernel is a set of Betty numbers. And now actually, let me just go, I'll just draw the actual map that we want to look at all levels as something like this. I'm just going to, sorry, it's taking me a little moment to do this. I normally do talks on the blackboard, but they kind of had to go the way of all flesh during the pandemic. So just stopping sharing for the moment here, we can get everything at once at all dimensions if we, if we diagonalize this matrix right here. So we just have a matrix that is on the off diagonal parts, it has the boundary map and its adjoint at each level. And we can now apply quantum phase estimation algorithm to this, and we can simultaneously get all representative of the homology at all orders k, and we can get the Betty numbers at all orders k, which is kind of great. Let me go back to sharing the screen. And actually, if you look at if you square that matrix I just got, you'll see that its on diagonal parts are in fact these things, just these things right here, the things in which we're trying to find the kernel. So we just this boundary map it's n sparse. This boundary map is n sparse, and that means that I can just use the quantum phase estimation algorithm to find things that are in the kernel. I just use a quantum phase estimation algorithm to find eigenstates of this operator and to evaluate their eigenvalue. And if the eigenvalue is 0, then they're in the kernel. And the corresponding eigenstates are then the representative of the homology. And then I can estimate the dimension of this kernel by just looking at the success probability. What's the success probability for projecting onto the kernel? And that will tell me the dimension of the kernel. So I apply the quantum phase estimation algorithm. I try to project my superposition of all simplices state onto this kernel. The probability of succeeding will then tell me the actual dimension of the kernel, and the resulting state is then some representative of the homology. And so this takes time order n cubed. That's using the quantum phase estimation algorithm, and the classical algorithm takes time order 2 to the 2 to the n, because that's the amount of time it takes to diagonalize these 2 to the n dimensional matrices, sparse matrices. So that's it. Let me summarize. We have, and I'm good, right? This is, and then we can start talking about it. I agree, it may have gone by a little fast. It's dense, it is. This is a quantum algorithm for doing algebraic topology. And the algorithm is going to find representatives of this persistent homology. And we create quantum superpositions of all these simplices. And our simplices, we're just mapping 2 to the n dimensional vectors onto n qubits. And our simplices has this very simple encoding that, simplex with, vertices. I just put 1s in the place where there are vertices of the simplex and 0s everywhere else. And then using standard methods of algebraic topology, I'm told that these are standards, these are standard methods. Then these representatives of homology correspond to super chains or superpositions of simplices that are themselves they're boundaryless, they have no boundary, but they are not the boundaries of stuff at one higher dimension. Those are the representatives of the homology. And so these turn out to be the eigenstates of the eigenvectors of this simplicial Laplacian, combinatorial Laplacian, because here, if you're in this, if you're not, if you're in the kernel this, you have, you are boundaryless. And if you're in the kernel this, you're not a boundary. And then the dimension of this kernel is just the Betty number at dimension k. And the eigenstates are the generators of the homology. Now, actually, so that's great. You solve this quantum algorithm solves this problem, and it takes order n cubed instead of order 2 to the 2 to the n. So it's definitely exponentially faster. But wait, there's more. Because in addition to getting the kernel of this combinatorial Laplacian tells us the representative of the homology in its dimension is the Betty number. But, you know, just for free, you get all the other eigenvalues and eigenvectors of the combinatorial Laplacian. These are actually called, they're often called the frequencies and harmonics of this combinatorial Laplacian, because these are the objects that go into this famous Mark Katz article called "Can You Hear the Shape of a Drum?" Right? If you know this, if you have the Mars cast the question, suppose you know the shape of a drum, then can you actually hear the shape of a drum? And so if I actually think of this object, let's see if I can get the object back here. If I think of this object as, you know, something that's kind of vibrating, or if I'm thinking of, say, other processes, geometric processes that take place on this simplicial complex. My favorite is like the vibrating simplicial complex. So you start solving, for instance, wave equations on this complex. Then these other eigenvalues of the combinatorial Laplacian, eigenvalues and eigenvectors of this combinatorial Laplacian, the things that are not in the kernel, give us geometric information of this, about this simplicial complex via Hodge theory. So it's great. It's I mean, and actually, I mean, there's since I'm not a mathematician, and the only thing I know about algebraic topology, apart from things like functor theory and stuff like that, is what I learned to write this paper. I am quite sure that someone like Arthur will be able, and other people in this audience will be able to think of other possible applications of quantum computing to algebraic topology, because let's face it, quantum computers are good at linear algebra. So, and I don't think that there's anything more to this talk. So I'm going to stop sharing and take some more questions.
So thank you very much, Lloyd, for beautiful exposition.
Oh, thank you. It was fun. I mean, it's not, I find this stuff difficult. You guys were troopers for hanging in there and asking the right questions.
So now we're open to questions, and would ask anybody who speaks to be sure their video is turned on.
Yes, so the obvious question is that which level of simplices you will decide. What's the advantage of doing k versus k plus 1 or k plus 2?
Oh, yeah. Okay. So in terms of, I'll answer in terms of applications, actually. So when people apply this to data, so this method of simplicial homology is in 2 dimensions, where you're looking at 2-dimensional surfaces in a 3-dimensional, embedded in a 3-dimensional world. Apparently I'm told that this is commonly used in animation. So that is, you want to, you know, animate, you're looking at the 2-dimensional surface of a 3-dimensional object. You're going to project it onto a 2-dimensional screen to animate it. And there's computational techniques work for, you know, essentially constructing the 2-dimensional surface of the object that you want to animate and then doing this projection. So actually, I mean, this makes sense. I don't know how, I've been told this by several people. So, but I don't know how true it is or not, but it certainly makes sense, right? that if I wanted to animate something, I'd probably make a simplicial complex of the two-dimensional surface of the thing I want to animate, and then move that thing around. And so, and keep, topological and geometrical information about that. And that, by the way, is the computational complexity, the classical computational complexity when k is 2 is a lot less than when k is larger. So when k is larger, the classical computational complexity just blows up because there's so many possible higher dimensional simplices.
So
The higher dimensional parts, then what the kind of thing that people apply this to are where you have very high dimensional data. So one place where I've read a number of papers about this is for financial time series that let me just draw something out. So I have, suppose I have n data points in a large data set where n is some huge number I'm looking at, and x could also be a vector of prices. So I have financial time series and I look at windows.
Seth, when we're not in mode where we see just your screen, it's impossible to read things you hold.
Oh, okay, sorry. Well, you could probably, if you go to view, I think if you went and viewed, if you could go and view speaker, you might be able to make that work. Let me see what happens if I do it. Okay, if I do view speaker,
Yeah,
well, I see you, Arthur. So, but maybe if you do view speaker, you might see me. If you do see me, well, I'll just describe it verbally. You just do the ordinary trick. If you have a time series, you embed it in a high dimensional vector space by saying, okay, I'm going to call x1 to up to x10 one data point in a 10-dimensional space, and then I'm going to call x2 up to x11 another data point, x3 up to x12 is another data point, x4 up to x13 is another data point. So I have a 10-dimensional window, and I embed using these delay coordinates. I embed these in a high-dimensional space. Except you actually are going to, you're going to take your data points are already multivariate, and you're going to look at longer windows. And so you now take your financial time series, you embed it in a very high dimensional space. And now this is a very common technique for financial analysis. And now you can do things like geometric analysis. You can toss it into a deep neural network. That's what everybody does these days. But you can also do things like geometric analysis and topological analysis in this high dimensional space. And actually, the topological analysis is interesting. You can see why this could be useful, right? Because if the market has different kinds of modes, right, that, like panic mode, or everything's regular okay mode, or a bull market or a bear market, then these will correspond to different kinds of subgroups within this high dimensional space. So for instance, a bull market will be some submanifold of states that may be quite distant from a bear market in this state. And so you can think of these as different connected components, and you might want to want to identify one thing that this topological method does is it identifies connected components within the space, right? That's kind of the lowest order simplices. And then the geometric information will actually give you the higher order eigenvalues, will tell you things about what's going to happen if you're going to, like, you're in a bull market, but now it's like about to go into a bear market. Then you'll be able to see the topology changing on the fly by applying these methods. That's, I think, in the high dimensional kinds of, that's an example where these methods are actually apparently quite commonly applied, according to my friends at Goldman Sachs. It's topology of data in high dimensional data sets can be a very useful object to get a handle on.
There are 2 questions in the chat for you to take a look
I
at.
see them now. Great, thanks. Okay, great. How do you get persistence? That is, how do you know if holes persist or disappear across scales? This is from Bernardo Amanero. Great question. Yeah, so what you do is, So remember, this simplicial complex depends upon the grouping scale. As I increase the epsilon, so I increase the grouping scale, I get more and more and more edges and simplices in the complex. Until, you know, if epsilon gets big enough so it contains all the points, then I just get one huge simplex where everything's connected to everything else. So the way that you look at the persistent homology is, well, first of all, for the Betti numbers, you just do this at different scales and you get the Betti numbers at different scales. But what you actually want for the persistent homology is you want to ask, if I have a representative of the persistent homology at a scale epsilon, then I increase the scale slightly. Then I'm going to ask, is this still a representative at the slightly higher scale? And if, you know, if I've got a hole or a void, let's say it's a hole, and I've got this chain that corresponds to the boundary of the hole, and I increase the scale slightly, the hole may, you know, close in a little bit, but I'm still going to have typically a high overlap between this representative of the homology at scale epsilon and at the scale epsilon prime, which is slightly larger. So is you can track these representatives of the homology as you increase the scale. Eventually, of course, the hole will get smaller and smaller and smaller and smaller, and finally it will just close up and go away. But if it persists over, you know, decades of grouping scales, which is what people are looking for in this persistent homology, then you should be able, once you've found a representative of the homology, you can track it to see if it's a representative of the homology at the next scale, the next scale, the next scale, and the next scale. So you can actually track these representatives as the scales shift. So did that help? Bernardo's not saying. Anyway, okay, good. So I'm gonna, in the absence of feedback from Bernardo on that. But does your algorithm track them? Okay, so in the algorithm, in the paper that the Nature paper, it does not track them. We didn't describe that, but in unpublished research that we've done since then we do track them, and we do it just in the way that I described. That is, it's and we actually, in fact, we realized this for the first paper, and I don't know why we didn't put it in there, but essentially that is, once you have a representative homology at scale epsilon, you can see by performing this, by trying to project it onto the kernel of the simplicial Laplacian, you can see whether it's still a representative of the next scale. And so that it's kind of like the for quantum mechanical people here, this is really the quantum Zeno effect, right? That is, you have a state, you project it on, I make a measurement, let's say, am I in the kernel here? And then I slightly perturb the kernel and make an almost the same measurement. And I see, am I still in the kernel of an almost the same measurement? And then am I still in this other kernel? And so it will actually project this state sequentially into the representative. So that's a great question. It's not trivial, as this answer kind of suggests, but that's the idea. So we have an algorithm that tracks them, but and you can figure out what that algorithm is if you look at how the algorithm works in our paper and then just like do the procedure that I just described verbally. All right, from not on the GAM, Vu to everybody. Hi, Professor Lloyd, I have a question about the Betti number. Is Betti number and persistent barcode the same thing? Because if we plot the Betti numbers versus many grouping scales, then we have a barcode-like diagram. Oh, great question. Thank you so much. Thank you, Nat. Yes, this is actually what people say in is what they call if you plot the Betti numbers over different scales, you get what's called a barcode. In fact, the barcode, you can think of it is the thickness of the bar is the Betti number at some scale. And then this bar, then as I change the scale, then I see if these Betti numbers persist. So it's called a barcode because, you know, here's, let's say, the Betti number, this scale, and then it persists. If the Betti number is roughly constant over many scales, I'll see this persisting, but then it will eventually go away. So in fact, in all these, for the reasons I gave before, at very small grouping scale, then the Betti numbers are all 0. And then what you hope is that they go up to a number that reflects the persistent homology. They stay roughly constant, and then they go away again at the end when everything's connected to each other. So that's called a barcode. And I didn't mention that, and I apologize for doing it. So this algorithm effectively is the algorithm for constructing the barcode for Betti numbers and persistent homology. For those of you who know the verbiage.
So I have a question.
Yes.
You've shown now in a beautiful way the connection of topology to quantum algorithms. Now, some more sophisticated notion in looking at surfaces is geometry. Does geometry also come into quantum algorithms?
That is a beautiful question, and I wish I knew the answer. When I explained this algorithm to Michael Friedman, who you know is a fields medalist in topology, he got super excited because actually it turned out that even though this persistent homology algorithm is normally associated, I forget the name of the what's the name of the guy at UC San Diego, he was a colleague of Michael Friedman's, but it turned out that Michael Friedman actually was the person who developed this persistent homology method for a secret DARPA program. And he got so excited that when I saw him, and I gave a talk about this at UC Santa Barbara some years, right, I guess it must have been around 2016 or 2017. He got really excited and he ran to his office and he got all the top secret documents in which he derived it and showed them to me. It's like, look. So I'm sure, since it's now well known and published, I'm sure it's fine. But he got very excited. And so he raised this question as well about its relationship to geometry, because he said, he had a very beautiful quote that he said, well, this should be related to geometry because topology is the discrete residue of geometry, which I thought was a very beautiful thing to say, even though I don't quite understand what it means. So yeah, I mean, there really ought to be methods that are associated with this. As I mentioned, I've been told by mathematicians that, the method that we applied is a method that's used in Hodge theory, and then these higher, as I mentioned, these higher non-zero eigenvalues of the combinatorial or simplicial Laplacian correspond to geometric kinds of objects. Michael Friedman suggested that it might also be related to Morse theory. And I would be very happy to work with anybody who wants to talk about this, who wants to explain Morse theory to me so that I understand it well enough so that we can make a quantum algorithm together. That would be awesome.
Are there other questions or comments?
Yeah, another question. So your algorithm predicts connected components. What about higher homotopical information? Can that be accessed by this algorithm?
Well, so the connected components are actually, the number of connected components is, I think that K is equal to 1 Betti number.
Okay.
And I forget how it shows up in terms of the representatives of the homology, but the K is 2 Betti number is a representative of the two-dimensional a two-dimensional hole is just a hole in a three-dimensional object. So the second Betti number counts the surfaces that bound holes in 3 dimensions. So they bound three-dimensional holes. So they're boundaryless, but they don't bound anything in the complex because they're bounding a hole, which by definition is not in the complex. And then the third order Betti number will count the number of three-dimensional surfaces which bound four-dimensional holes in the four-dimensional objects, and et cetera. So it does in fact access the higher dimensional homological information. But in terms of homotopy, I don't know. I mean, there's lots of I've been told that maybe these techniques could be used to do cohomology as well, which makes, of course, complete sense. But I don't know how to do that. I'm full of lack of answers to questions about algebraic topology.
Well, thank you so much, Seth, for really interesting numbers of questions you've raised. And I think a good seminar leads to a new collaboration, and there's several potential new collaborations here.
Shoot me an email here. So here's my email. Anybody who wants to work on this, that's me. Don't send me spam. but anybody who wants to send suggestions about where one might be able to extend this work, and in particular, if you send something like to me about Morse theory and give me something to read, then I'll try to read it, and I'll probably fail, but at least I'll try, and then I'll know who to ask questions to.
Well, thank you again, Seth, and bye-bye. See everybody next week.
Thank you. It's an honor to be able to participate in this seminar. I've got to say, it's a great seminar. So I'm honored to be able to be here. Thank you.
Thank you, Seth.